Well, hello. This is Peak Info recording a video for you. I'd like to discuss a challenge problem that was presented to me in a classroom setting recently, and it's the electric field of an infinite line of charge in the y direction, but only finite length in the x direction, and having width L centered on X, and basically we'd like to find the electric field of that. So this is problem 26.67. So chapter 26, challenge problem number 67 in Knight's textbook, 3rd edition. So I'd like to discuss this for you. So hopefully I can move forward here. All right. So looks like this is the setup of the problem, that there is a sheet with an infinite line of charge. So hopefully you can see my pointer here. There's this sheet, and it goes off forever in the y direction, so that's towards infinity, and also the negative y direction. And then it's centered on the origin, that's 0 right here, and let's just assume it is uniformly charged with positive charges, just like shown. Now, the electric field would just be in the exact opposite direction if it were negatively charged. So we're just going to do this entire problem as if it were positively charged, knowing that we just have to literally change the sign and thus change the direction to exactly opposite anti-parallel if it were negatively charged. But anyway, we'll perform that sort of setup, and then also we'll sort of focus on this little strip or this little line of charge as part of the whole sheet, and that's because that will be a representative line of charge, but then the sheet is just, of course, made of many of these strips, or sort of many of these lines, if you shrink the strip down to a infinitesimally thin line. So we'll get to that. So also notice that we have defined an x and y axis that, again, the sheet is centered at the origin at 0, 0 in terms of x and y. And then also we've chosen a point D. So this is the point D out to here. The point D is exactly D units to the right of the origin. So it's not an x coordinate yet, it's just some arbitrary point we're choosing out here at point D. And then we're also saying that that strip that we were focusing on is at location X. And X is somewhere along the sheet, and it's just some location X away from the origin. And so that we'll get to this distance, but this distance, if we call the distance between the strip and the point D, if we call that distance r, like a radius, then that'll end up being d minus x. So if the entire distance is d, if the distance to the strip is x, then d minus x, which is the radius, will be that distance between the two of them. Okay, so let's proceed forward and set up the mathematics of this problem. So I'll go ahead and read the problem out of the Knight textbook, which says the following. So an infinitely long sheet of charge with width L lies in the xy plane between x equals negative L over 2 and x equals L over 2. The surface charge density is eta. Derive an expression for the electric field E vector at height z above the center line of the sheet. So I actually read the wrong problem. Let me read the correct problem. That was problem 66. So what I meant to say is an infinitely long sheet of charge of width L lies in the xy plane between x equals negative L over 2 and x equals L over 2. The surface charge density is eta. Derive an expression for the electric field E vector along the x-axis for points outside the sheet. In other words, x greater than L divided by 2. So x larger than 1/2 the sheet width. Part B, we're supposed to verify that the expression has the expected behavior for x much, much greater than L. In other words, very long distances away from the sheet along the x-axis. And then part C, we're supposed to graph the field strength E versus x for x greater than L over 2. Okay. So how are we going to solve this problem? So we'll consider a point on the x-axis that's, again, a distance d from the center to the right of the sheet of charge, so that it's d is that arbitrary x coordinate, but we don't want d to be confused with x, because we're only going to let x, in terms of things we add up, go along the sheet itself. So d is to be disambiguated from x, not to be confused. And let's just let d be a constant for now, because we'll find the electric field at that point d, but then at the very end we'll allow d to vary, because d could be anywhere outside the sheet. So that'll become clear as we go along. The total charge on the labeled strip, so let me go back to the strip there. So the total charge on this strip here should be given in terms of units of coulombs. So that means Q on the line should be, let's see, it should be eta times y line times delta x. So how do we get that? Well, let me write down on here. So eta, let me increase the thickness of my writing implement here a little bit. And then I'll erase. Okay, back to here. So better. Okay, so eta is equal to the surface charge per density. So that's charge per area. So this has units of coulombs per meter squared, and that has to be charge Q divided by area. So what that means is we should be able to take eta times some sort of a length and some sort of a width. Okay. Well, we know that the width is L, and we know the length is the entire length of the y-axis. So we'll say this is, let's see, L times y total. Okay, so hopefully you kind of understand where I got that from. So that's how we get this expression, and let's just call y line the length of the entire line, because y is basically the length in the entire y-axis, and that's the total charge. So notice that if that's the total charge, we want to figure out the influence of the electric field just from one strip of charge or just one line of charge, and then add up all those strips. So think of a strip as having a finite width, but think of a line as just having a width that is infinitesimally small. So we're going to need to leverage also in this problem the electric field from an infinite line of charge. Now, why is that? Well, we could think about taking, let me go back to the drawing here. We could think about, I'll go on to the next page here. Whenever we have a continuous line of charge, we need to think about taking the integral. So the integral of Ke, that's the Coulomb's constant, dq, sorry for the bad handwriting, it's not my best, over r squared. But notice that in our case, when we would go through this, we would have to get the expression for an infinite line of charge and then add up all those infinite lines of charge together along the x-axis. And that's because, basically, we need to basically perform an area integral, but we know that the first integral along the y-axis will basically give us the equation for the electric field coming from an infinite line of charge, where the line has infinitesimally small thickness along x. So this is one way to get an electric field, is to take this integral, but we would like to replace this integral with still another integral, but an easier integral, because that would be basically a much easier integral to perform instead of performing a full double integral. Okay, so that's kind of what we'll do in the problem here. So we want to leverage this expression for E, an infinite line of charge electric field, in terms of the Coulomb's constant, lambda, which is the linear charge density. And by the way, just so we're clear, linear charge density lambda has units of coulombs per meter. Okay, that's terrible. Let me try that again. Maybe I can just do undo. That's better. Coulombs per meter. Okay, so that's the units of lambda. Okay, and by the way, I mean, the lambda is not wavelength here. It's linear charge density, so you might consider putting a different font on it. In any case, lambda is the linear charge density. So we want to see if we can leverage that solution. This is something you can look up in a lot of textbooks. Okay, so Ke again is the Coulomb's electric constant, so about a value of 9 times 10 to the 9th Newton meter squared per Coulomb squared. R is the distance away from the line of charge. So what let's do is let's take this Q line equals eta times y line delta x, and let's solve for lambda line, and then let's get lambda on an infinitely thin line of charge. So that's what we'll do here on the next slide. Whoop. Next slide. So we'll take Q line divided by Y line, and that will give us units of coulombs per meter. But coulombs per meter are going to be the charge per length just on some strip of small but finite thickness. So that's eta delta x. So if we go back a couple slides, this lambda is the charge per length along this thin strip. The charge per length along this thin strip. Okay. So then we go to eta times delta x, because notice that eta times delta x will also be units of coulombs per meter, and that comes from the previous equation. So we take the differential of both sides of this. So a differential means we shrink things down to infinitesimal size. So lambda is not lambda of just like a strip, it's lambda of a line, and the line has infinitesimally small width, and that's eta times dx. Okay. So the idea is that each line has linear charge density eta dx equal to lambda, and we should be able to add up all those lines, and adding them all up, if it's a continuous charge distribution, means taking an integral. So Here we have that integral that I showed when I was hand sketching before, and that is E equals KE integral of dq over r squared. But we know that this is KE integral 2 lambda over r for a infinitely long line of charge. But notice that we have multiple lines here. So it's not just 2 lambda over r and we're done. It's integral of 2 lambda over r. So lambda gets replaced with eta dx because they have the same units, and we expressed why that should be the case. We can move any constants out front, and then we need to think about what r is, what that radius is. So recall that I defined that the radius should be the distance between that strip, or if it's shrunk down in width, that line, and the point D, which, remember, D is like an x coordinate. We're just letting it be a constant value because we're solving for the electric field at just some point D for now. And remember that r should be d minus x because x is how the current location of the strip or the line from the origin on the sheet that of interest where you're looking at the charge influence on the electric field from. Okay, so we would really like x to go between negative L over 2 and positive L over 2 because that's the most natural bounds we could think about because those are symmetric bounds, and the sheet is centered on the origin, and it's we would like to be able to integrate in terms of x. X is very natural in terms of calculus to integrate in terms of, and that's on the x-axis. So we would like to have those as our bounds of integration. So let's let r be d minus x. We can take eta outside of this integral above because it's a constant, and we should be able to get the integral in vector form as shown here. Okay, so let me see if I can move my image up there. Okay, probably get this a little better. Stand by. Okay, so even better. So what do we have? We have so I can't take my image up too far. So it looks like we have E vector is 2ke eta integral of negative L over 2 to L over 2 dx over d minus x I hat. I hat is the, of course, unit vector in the x direction. So it has magnitude 1, direction x. Okay, and then if you recall from your calculus classes, the derivative of a variable over basically itself is like a fractional change, and you integrate all those fractional changes, that is essentially a natural logarithm. And by using our bounds of integration, we're going to use a property of logarithms in a moment, that a subtraction of logarithms can be turned into a division. So the integral of dx over d minus x should be negative ln of d minus x. The constants stay out front. The bounds of integration are negative L over 2 to positive L over 2, up, lower and upper. I hat makes the vector. So we can bring this minus sign out front, and then we substitute in our bounds. We're using the fundamental theorem of calculus because we're doing upper minus lower. I hat is still there. And then we can use the division. So this is essentially going to be, let's see. So the minus sign can be brought back in. So this is going to be natural log of d plus L over 2 minus natural log of d minus L over 2 if there's no negative sign out front. But then let's multiply the top of this newly formed fraction by 2 and the bottom of this newly formed fraction by 2. And you can do that because 2 over 2 is just another form of 1. So 2 times d is 2d, and 2 times L over 2 just gives L. So the form just looks a lot more compact. You get 2d plus L over 2d minus L. I hat and that's inside the natural logarithm, times I hat makes it a vector. 2ke eta are the constants out front. And then lastly, we want to make the following recognition. We want to recognize that D is our x coordinate. Because if you recall, let me go back here, really, D is the distance from the origin to some arbitrary point. And we're looking at the electric field at that arbitrary point. And if you recall, we said that, well, we can do this for this arbitrary point, but we want to allow there to be any point outside the sheet. So if we allow any point outside the sheet, that's really an x coordinate coming from the origin. So we get exactly the following. We just take that D from the previous equation and just go ahead and call it x. Now again, the reason we didn't call this x in the first place is because that would have confused in terms of x, the integrating variable. But if you replace D with x, we should have 2ke eta natural logarithm of 2x plus L over 2x minus L. I hat direction, that's the unit vector, and that's the electric field vector for an infinite sheet of charge that's infinite in one dimension, where the width is L centered on the origin, and this is the electric field on the axis. Where x is greater than L over 2. So x is larger than past halfway of the sheet. Okay, hope that makes sense, because that was definitely the hardest part of the problem. Okay, so I'll move my image up here. So now part B of the solution says the following. We are given the approximation and the hint that if u is much, much smaller than 1, then the natural logarithm of 1 plus u is approximately u. So we have to use this property of natural logarithms. Okay? And what we're going to see is that if we take our solution in part A, we're going to allow x to be much, much greater than L. So conceptually, let us think about this. If we're very far away from the sheet of charge, then x is much, much larger than L. So there's this sheet that goes infinitely in one direction, but has a very finite width. If we move far away from that sheet, we're basically saying that the width is no longer substantial, and that the width of the sheet is more like just a line of charge. So we expect that the expression we had found before for the electric field coming from an infinite line of charge is what we should approach if x gets much, much larger than L. And furthermore, to use this approximation of ln 1 plus u approximately u, we have to go back to this logarithm property that we had before and go backwards, and then we have to write things in terms of sort of like a 1 plus u. So how are we going to do that? Well, what we'll do is we'll take that electric field expression we had before, break the division down into the subtraction, but then let us try to come up with 1s for the first terms and then L over 2x's for the other terms. So we can arbitrarily divide each argument of these natural logs by 2x on the inside, because it's just like, again, multiplying the entire argument there by yeah, I'm trying to think, like you can do that because you can imagine that if I took this expression and I multiplied by 2x, I would get 2x plus L. So if I divide by this, I would get L over 2x. So I'll have to think about why that is. Maybe I'll do an edit in the video later. But in any case, this is what we get for the expression. Okay? So notice that this is unitless, this is unitless. But notice that 2x is going to be much, much larger than L, So that means this, which is like our u, is going to be very, very small as x gets much, much larger than L. So basically, ln of 1 plus L over 2x will approach L over 2x. And then likewise, this second term will approach minus L over 2x. Okay. And then the idea is that that's the approximate value of the electric field when x is very large. Okay, so minus minus, of course, makes positive. Common denominator, you add 2L over 2x, but then that's just L over x. And then if we bring the eta up, we can think about that eta times L. We can go back to what we were thinking before and then reassemble that eta times L. So this delta x is like L now because it's just the full length of the, full width of the sheet. And that should be like a lambda. That should be like the charge per unit length. But that's the charge per unit length for the whole sheet. But the whole sheet is so far away now, it's like the charge per unit length of just a line. And when I say a line, I mean an infinitesimally small line, so just lambda only. So the idea is that we get eta times L is like lambda, and then 2 can come up here because it's just commutative. This is like 2 over 1, so you get 2 lambda over x times ke and an I hat. Notice that this is the electric field for an infinite line of charge. So we already saw this before. So notice that the only difference from what we had before is now it's got an I hat, just because it's a vector. And notice that x here is the distance away from the origin, but you could think of x as approximately r, that radius, if we're very, very, very far away from the the sheet of charge, which has very small width compared to the distance we are away. And then again, we're letting this lambda line, which we call just the charge per unit length of the strip, we're letting it be the full lambda because we're saying the width of the whole sheet is very, very small. So the entire thing looks like an infinite line of charge. Okay, so that's what it should approach, and that kind of makes sense. And lastly, part C of the solution. The table in the graph on the next slide summarizes the dependence of the electric field in the x direction. And let's show that here. So note that here in the, let me see if I can make this a little easier to see as I'm narrating here. Sorry about that. Stand by. Sorry. Okay, better. So, yeah, like I was saying, so this is kind of the dimensionless length away from the sheet. Okay, so notice that we can't have any values of x divided by L. We can't have any values at 1/2 or 0.5 or lower, because if x equals positive L over 2, then that would just be 1/2. So the first value we have plotted here is 0.75. And if we have 0.75 of x over L, then we can think about plugging that in to our previous expression, and we'll essentially get this. This is kind of like our dimensionless electric field, if you will, because, again, the electric field depends upon 2ke and eta, and this expression, or previously this expression. So anyway, we'll do it over lambda. Yeah, so this is the expression we should get. Notice that it looks like the curve, basically 1 over x from calculus, but notice that it falls off at a 1 over x dependence. Okay, so again, x is like the fall off rate like a radius, and notice that it falls off as a reciprocal function. Okay, so you'd expect that if we're 4 times the distance away that we were at L, so we would be at 1/4 of what we are at up here. Okay, so hopefully that makes sense. That kind of solves the problem. It took me a while to solve this problem and to get the solution ready for this video, but I hope that was helpful. So I want to thank you for your attention. This is a new YouTube channel and hopefully an otherwise channel of videos. So I'm Peak Info, giving you all your assistance in many things: math, statistics, science, calculus, atmospheric science, meteorology, all kinds of things. So education is my real passion. I just really appreciate your time and watching this video. Please like, share this video, and please subscribe to the channel. And you can send an email to highpeakeducation@gmail.com, and then our website coming soon at highpeakeducation.com. Okay, thank you very much, and I hope to see you in the next video.